Hey guys, how's it going? Today we're doing our final live stream of Terms 2 projects, which is MPC. So I'm Aaron Brown.
I'm Dominique Luna.
And we're just going to walk through the project. We're going to try to look for any pitfalls that you might run into. So first of all, what is the MPC project? So Model Predictive Controller. How is it different from the PID? And we got this cool optimizer that Dom worked on that kind of allows us to do some pretty fun stuff with that. So that IPOP-T, it's handling all your constraints. It's handling how you're doing the transition of the object through space. And it's pretty fun to work on.
Yeah. I mean, it was pretty fun to work on. It was pretty tricky to get it all to work together. But I think we made it so it's fairly okay to use. Yeah, but that's what we're going to do today. We're going to sort of walk through that code and
so
make sure. Yeah.
Let's go ahead and boot that up. Currently sharing my screen. So the first to start off with, I just kind of like grab the project, which is kind of over in this GitHub repository, like always, this MPC project. Come over here. And really, there's probably two files that you'll mostly be working on for this one. So if I go ahead and take a look in SRC, the main ones that we'll be working on is main.cpp and mpc.cpp. So let's go ahead and open main.cpp because this is going to be our main interface. This is what's communicating with the simulator with our C++ code right here. So when we first open this up, we have some kind of nice functions that we'll be working with. So this is the polyeval and polyfit. So the reason we have those is one of the main things that we're going to be giving to MPC is, so we're kind of like talking about this and how to really sum up what MPC is doing. We have this objective, and basically it kind of comes down to like two objectives. The first one is speed and how fast do we want the car to be going. And so we have a cost function that measures that. So it's if it's doing really well, the speed of the car is really close to the desired speed. And then the other objective that we're trying to meet is we want to follow this line. And we get that by inserting these waypoints. So we're just kind of looking out in the future, and we have these 6 waypoints. And with this polynomial, we're able to fit a polynomial through these 6 waypoints. And if the car is doing well, it's close to that line. It's following that line. So that's kind of our two objectives when we're looking at the MPC, and we'll be looking at that later with defining our cost function. For this solution, we're not going to look at the delay because we don't want to give all the secrets away. So we're just kind of do a basic solution that doesn't worry about delay, but then we'll talk about how you might deal with delay and what you need to do in order to do that. So our code starts in here, and what we're getting from the simulator, those are those 6 waypoints, the X and Y coordinates of those waypoints that we were just talking about before. We also have the X and Y position of the car, and we have the car's psi, its the angle, and its speed. So yeah, so we have these waypoints, great. So what do we kind of want to do next, Dom?
Right, so now that you have the waypoints, well, there's a bunch of things that you can do, but what we ended up doing in this solution was first, we subtract all the points from our current position. So here it's points x minus px, points y minus py, and that means the x coordinate will be at 0 and the y coordinate will also be at 0. And that just simplifies things a little bit for us. The next simplification that we do is we want to make psi 0 as well. And in order to do that, we rotate all of our points, which is shown here. So this is sort of the mathematics to do that.
Right. So this equation right here is actually going to be doing a rotation about the origin. So for example, say your car is sitting at like 45 degrees. We want to rotate it to the right. So we're going to do minus, because the way this is set up is the angle within the cosine and sine here will rotate to the left. So we do the negative of that to actually rotate down. So then our reference system has 0 degrees, and it's also sitting at the origin. We do this for a couple of reasons. It'll help us with doing our polynomial fit, because then most of the time the car is actually the same orientation as the line. So it'll be a horizontal-ish line that we're looking at. And that's nice when we're doing a polynomial fit. Polynomial fit gets more difficult if you're doing something that's mostly vertical, because it could maybe not be a function and you can have multiple values. On the x that have or multiple y's that have the same x, and so that would cause problems there. Also, it's going to help with the mathematics of doing like the MPC evaluation, and help us try to look at some cross-track error and just doing the transitions in general. So we're shifting to this reference angle, and that's something that you can choose to do. If you don't do it, I think you'd end up doing a lot of different transformations anyway.
Right. Yeah.
So after I do that, I want to use that polyfit function, but it's taking in this eigenvector xt. So this is just one way I found of doing a conversion from like this vector double, I believe it was, into this kind of vector xt. So I kind of do some pointer magic here and pass it that, and then
points x/transform. Yeah.
Yeah, and then there's 6 elements in there. So that'll convert my vector double to this eigenvector xt. And then I can pass in the polyfit. And from there, I have the coefficients of a third order polynomial.
Right, that's the 3 there.
Yeah. So next, I'm just kind of like calculating what CTE and the error psi values are. We kind of put some notes down on here. So we mentioned that we were doing this at 0, so we shifted everything. So now the car is at 0, 0, and its angle is also at 0. So we're talking about the very initial point, so that we're just passing 0 into the poly eval with those coefficients that we found. We'll get a y value, which actually we're doing our estimation of CTE. It's important to note that's like not truly the CTE, which would be like the shortest distance of the point or the car's point to the polynomial. But in this case, we kind of changed it to be horizontal, which this works pretty well unless there's like a lot of warpage, but still it ends up working pretty well for the cost function.
Yeah, yeah.
So we'll just do that.
Oh, well.
If you're very adventurous, you could try to mathematically get the true like cross-track error, which is the shortest distance from the point to the polynomial. This is
the error psi.
Yeah, so the error psi, we left some comments up here. So our psi now is 0, so it's 0 minus.
So comment this one out so it's easier to see.
Oh yeah.
Right. Okay. Right. So the second line here that I'm on right now, this is a simplification of the first line. But right. So this is the full line that we have here. But remember, we made psi 0, and we also made px 0. So this is 0. Px is 0. So this term here becomes 0, and this term here also becomes 0. So what we're left with is just this guy right here. So that out again.
Yeah.
And yeah.
So that's the error. That's the difference in our psi versus what the path's angle should be. So that's what that tan is just looking at. It's looking at the angle of that, of the slope, the tangent line on that polynomial. And that's the difference. we want that to be 0. We want cross-track error also to be 0. So steer value, that's actually well, some extra things that the simulator is giving us, steering angle and throttle.
Right.
You could use this to try to, if you had a delay, to try to estimate what, like, forward in time those that state vector would be. Although it's kind of an estimation in a lot of ways, because this throttle is not the same thing as acceleration, for instance. But for low delays, I found that it actually is a nice estimator, because we're not really truly given the acceleration of the car. You could build that in Unity, and you'll actually see some things in future projects where you're looking at the acceleration. But here, let's not worry about that too much. Let's talk about the state that we have right now. So we have X, Y, and theta, and they are all 0 now because of our transformations that were happening up above. We have our velocity that's given to us from the simulator, and we just calculated CTE and error psi. Cool. So yeah.
Now we have our state. So now we pass it into model predictive control, right?
Yep, and our coefficients as well, which is that path that it wants to follow. So
right.
It's used to help figure out how far away it is from the path.
Right, and we pass the coefficients because we're going to need to calculate the future cross-track error, and and
the error psi.
Right, yeah. So yeah, we're going to have to calculate those values in the future, and that's why we pass the coefficient vector as well.
Yeah, and we kind of define what it's returning to us with this vars that we're using. We get to kind of go into the function here and pick it. But what's going on here is we have these next X and Y values, and they are used to just do some visual debugging, and it gives us nice visual effect of what the line that you're trying to follow. And that's created from the waypoints. So it's like, it could be from the polynomial fit. In this case, I am using that polynomial fit. I'm just kind of going out to set amount of distance in the X, and I'm defining it for, I want to see 25 points out in the future. And then I'll just, I'll pick that X as it increments along and push it back into next X vals. For next Y vals, I'm just running the poly eval with the coefficients that I calculated and that same X that's being used above. So that gives me this nice, so this is a yellow line, and it gives me this nice, the line going through the waypoints in the simulator. So that's the line I want to be close to, I want to follow. Next is a green line, and that's this MPC, and this is again X and Y values. And I'm actually fetching these from the vars that I got. And the way I'm returning vars is that every even value will be an X, and every odd value will be a Y. And I'm pushing that onto my MPC X and Ys. And finally, I can just sort of tell the simulator, here's my next X vals and MPC X vals. Go ahead and graph those for me. And then, of course, get a steering angle and throttle, which are some of the first things that vars is going to return. Those are the main things that we're interested in. These are just for like graphical niceness, but this is actually what's going to make the car drive and work well, going fast and following that curve.
Right.
So cool. That's basically all of main.cpp. Kind of things that we went over. So were how to kind of calculate cross-track error and the error psi, do the polynomial fit, and the big thing kind of was doing this transformation into this different orientation space.
Yeah, it makes it work quite a bit.
Yeah, it makes your job easier, I guess. Yeah. So the next thing is kind of look at MPC. So
okay, so first thing here, you have your n and your dt, right? So this is the time step length, and this is the duration. Why did you set this to 10 and this to 0.1?
I found that maybe at first it seems like having a large 10 would be nice, but actually it's kind of more computationally difficult for the system because it has to go further out in time, and also makes the cost function have to work harder too. Like it might be more willing to risk something crazy that you on a short term it wouldn't have to, but on the long term it's like I have no choice but to do this and throw you off the track.
Right.
So actually just having a 10 like that was nice. To be honest, I just did it experimentally. I pick a 10 of an N of 20, and it's like, no, it's more willing to go off the track and it's taking longer to compute. Do an N of around 10 and it works nicer. Also DT, you want to be careful because you don't want that to be too small, or that it has to run just more steps, and that's more computationally difficult. But you don't want it to be too small either, because then things are happening not as quickly as they could be.
Okay.
So this is going 1 second into the future is what this ends up being with N 10 times 0.1.
0.1, right.
Yeah.
Cool.
Found that to be nice combo.
All right. So the next value here is LF. You don't have to worry too much about this one. This is a constant set for you.
But how did you calculate it, Dom?
Yeah, so I ran a simulator with a constant speed and steering value. And then I also had a simple Python program that sort of did the same thing based on the equations that we presented during the lectures. And I compared the two, and so the only really tuning parameter that you have to change the behavior is this guy right here. And so I essentially just tuned him, or tuned it until it reached 2.67. And then it turned out that the circle in the simulator, yeah, because we're going, so what happens if we set a constant steering and a constant speed is we end up going around in a circle, right? And so, and yeah, so setting this value to 2.67 made the circles the same.
Yeah, so you could run that simulator for multiple different combinations of speed, constant speed, and constant steering, and it would be an accurate representation of how that vehicle would move. So the LF comes about because you have a car and it's a different length. So if it's a really wide car, like a limousine, it's going to have a different LF than, say, like a super short car like a Mini Cooper.
Right, yeah.
So, and then right here we say like this LG is a representative of the length from the front to center of gravity that has a similar radius.
Right.
So it's interesting because if you kind of look at the simulator here and you kind of measure it out, like this looks about the front, and this is 1 meter, 2 meters, 2.7. It's like right about the center. So in Unity, I think this is like constantly the same mass, so center of gravity should just be in about the center, and interestingly, it looks like it about does, so it's cool.
Yeah.
So, but yeah, most actual companies working on figuring out what the LFR with an actual car will be running those same experiments that Dom was talking about, running it in a track with a constant velocity and steering, and making sure this LF chosen models it.
Right. Yeah, their models are a little bit more complicated, so they have more parameters. But yeah, that's pretty much what they do.
Yeah. So next we kind of have this like ref cross-track error, ref error psi, and ref v. These are all things that we want. They're all part of our objectives. So we want that cross-track error to be 0. We want that error psi to be 0. So we want the car to be right on the line. We want the car to align right on the line, right along with the line. And then the ref v, make it fast.
You don't have to make it fast, but
yeah, it's fun.
You might want to.
So there's that. There's like all these sizes that kind of prepares one of the vectors and how to add access it and address it in memory.
Yeah, right. Because so we have to pass all of this as a one-dimensional vector, and so right, and so we want to sort of know when one part of the state starts and when, when one part of the state starts, and that's essentially sort of it.
Since that's essentially what we're working with right there. So let's kind of like dig into some of this more of this FG eval. Kind of have this operator function that we get to use later, where we have this FG that's just kind of describing some constraints that we have on the system, as well as vars. And as we go through, so FG0 is the cost function, right? Everything is being stored on there. And then we update our cost function somehow. Basically, a lot of this I sort of just copied from the classroom. That was pretty helpful with getting stuff to work.
So the solution to the quiz, I mean, what you'll end up doing is probably just copying that and then working from there. And and so this is basically what was in that solution. It's just tuned a bit.
Right. So one thing to know is that these coefficients have a lot of power on how much attention you want the cost function to pay to certain attributes. So right here, I'm making these really high. That means that I really want my cross-track error and error side to be low. So it'll pay a lot of attention to that. This is more attention than, say, speed. So then it's not as willing to go fast if it's going to hurt itself in the process and go off the road or get really misaligned with the track. And these other are just very moderate. This was kind of nice too, this high power, because that's like how smooth your steering angle is, and you don't want that to be too jerky at all. Right. Because that could really compromise the car as well. And so that's kind of the cost function right there. It's pretty intuitive on how you're setting those coefficients, I think. Kind of more about the structure here. We're just kind of going about setting up the FG. And once again, a lot of this is kind of defined in the quiz. I think when I was kind of like porting it over, a lot of the code is already in the quiz that really help out. But this is kind of just describing how FG should act based on the vars that it's given right here. Right. So then we kind of go into some of our constraints for our system. And what's important here is the transitions that we're actually making.
Right. So the values right here. So these are the values at time t+1, the values of our state, of our model, and these are the values at time t. And so then basically, and then here as well, so we calculate the polynomial value, which we do because we have the coefficients that we passed in, we previously talked about. So this is our, the polynomial value. This is our desired psi value, and we're going to use these to calculate the cross-check error and the psi error down here. And these are essentially the model equations that we showed in the classroom, right?
Yeah.
Right. So what we're doing here is we're enforcing. So here we have the value. So at time t+1, and this is the value at time t. But then this part here is how this changes. And what we're enforcing is the value at time t+1 has to be equal to the value at the previous time step plus the rate of change here.
Yeah, and then later on we assert that has to be 0 because those need to be equal to x1 and everything to the right of it there. And just doing x1 minus that's another way of saying that, and then making that and force that to be 0.
Right. Otherwise, the solver might do some weird stuff, and our solution won't end up that great.
Yeah, and this CPPAD is some special library that helps us do all the like gradients and linear algebra that we need in order to...
Right. So basically, it calculates all that for us, so we don't have to worry about it. Sort of, if you remember TensorFlow, it's sort of similar to that, where it calculates the derivatives for you.
Yeah. So that's really cool. It's helpful to have. Here's the solve function. So that's what we're kind of seeing in main.cpp. We're calling that on our state and coefficients. So let's go ahead and pass that in. We have our state is defined right here, and we have to set it to a certain size. And there's this nice little equation in order to do that.
Right. So that's the number of time steps. We have sort of 6 parts to our state. We have x, y, psi, v, the cross-track error, and the psi error. And then we also have, and then n minus 1 times 2, that takes care of delta and the acceleration a as well. And it's n minus 1.
Doesn't deal with the endpoints at all.
Right.
So you're not having a delta at the very end. It's just, you don't know where you're going after that. So you don't have to worry about it.
Yeah, so it's 1 minus n, essentially, right?
Yeah.
So then, and then the number of constraints. So basically, we have our 6 equations, and then we're running the solution for 10 time steps. So we're gonna
generate 60 of n constraints.
Right, and then so here, this is d vector is a vector of doubles, so that we define here, and it's a special vector from CPP AD. Don't have to concern ourselves too much about that. But so here we initialize all the variables to 0, and so these are the variable lower bounds and the variable upper bounds, and they're the same number of so they're also the same number of variables as this vector here. And
I guess this next part's where things get a little bit interesting. We can actually set some limitations on how the simulator is moving about.
Right, so here, so this is, so I up until less than delta start. So essentially, this is going to set the lower bounds and upper bounds for x, y, psi, v, cross-check error, and psi error. And we're setting those lower and upper bounds to
really big and really small numbers.
Really big and really small values, because we don't really care too much what they are. That's not really what we're concerned about constraining here. So over here, we set the delta. So I actually think.
Yeah, there's a couple different ways of doing this one. Yeah, it's interesting because we just tested this one out and it worked just as well.
Right. So there's several different ways you could set these. Right. So this is the bounds under delta, and I actually think there's a typo here. This should be here, and this should be over here.
Well, let's maybe talk why both of these kind of work.
Yeah, I guess we could.
Well, oh, maybe it still works. So right here, I'm kind of setting the angle, and basically I did a calculation of 25 degrees to radians,
Right.
and that's how I got this.
And the 25 degrees comes from the simulator, which can only turn, which will has a cap of being able to turn 25 degrees to the left or 25 degrees to the right.
Yeah.
And so that's where that value comes from.
And the LF is just there because we'll end up dividing by it later, and it'll make it so we're actually truly going 25 or minus 25 degrees.
Right. And
then there's acceleration here.
Acceleration, yeah. So this is just a simplified sort of calculation for it that works quite well. We set, we're setting the lower bound on acceleration to -1 and the upper bound to 1.
Which seems about right. I mean, yeah, it's just an estimation. We're not really sure. I kind of have driven the car around in the simulator and like tested it, and like its max acceleration seems to be about like 5 meters per second squared, and then has more deacceleration when it's braking, like around -12. But
right. So that's
I guess this isn't actually acceleration. This is just like the actuators version of it.
Yeah.
So let's continue, and we got some constraints for the lower bounds, and we just set these exactly the same, and this is just our initial value. So it's just a special thing we have to do for the initial start points.
Right. So
they have the same upper and lower. They can't change.
Yeah. So we're setting all our constraints so that the lower bound is 0 and the upper bound is also 0. But we make a special case for our first state. So we set all those values to the initial state that we passed in. And if we don't do that, then the solver doesn't really know where to start from. So say our velocity should be 0, but our reference velocity, well, in this case, it's 100. The solver will just set it to 100 right away. And so clearly that will cause problems. If the velocity is not actually 0, which it won't be in the simulator. So
then finally, we call this FG eval with the coefficients we have here.
Right. So we create the object there. And down here, these are. So the one to pay attention here, and you probably won't have to change it, but it's max CPU time. So currently we have it set to 0.5, which is half a second. And that means that after half a second, the solver will return with whatever solution that it currently has. And the reason why you might want to change this is because we are working in a simulator that is sending values back quite quickly. I think it's about...
Oh, it's like 20 milliseconds.
Right. So
50 frames per second.
Right. So you don't want to, wait too long to compute your solution. So you might want to change this depending on how you're calculating your solution. And the value that will play a big part there is, if we scroll back up to the top of the file, it's this value here. So if we make this larger, then the solver will take more time to compute the solution, and then that's where things might be problematic, that you might have to restrict the amount of time that it takes to solve it. But in this case, we set n to 10, which is relatively small, and so we don't really have to change this value too much. But you might want to, depending on your solution. So it's just something to keep in mind.
Okay. So we kind of come down here, and this is what we're really interested in, is returning this result. The way I kind of have it set up here is I'm declaring this vector double result. And I want to push back, so this solution kind of came about here, and it derives a solution. And it has this delta start and this A start. And those are going to be the steering and the actuation that I need to do in the next time step. And so those are kind of important. So that's what the car should do, to actually, do what the MPC controller's best solution was. And then I'm just interested in capturing where that MPC is going to be in the future. So there's these other values. So the solution X start, and it's kind of at this address right here with X start and Y start. So I'm just grabbing the solution's X and Y coordinates for where the MPC controller is going. And that's the green line, and that'll give me a nice kind of view of where the car will be in the future. And I return that result, and we've actually made it all the way through this MPC.cpp.
Yeah,
I guess
it's quite a journey. But
we'll go ahead and save it. So we're kind of talking earlier about some of these constraints right here. We tried changing one of them, and this actually ends up being quite similar to -1,1, because LF is like 2.67, so it's actually pretty close. So we changed it before, it was pretty similar,
right?
But let's go ahead and maybe check out what it looks like if we run it. So for running these, you kind of create a build. So make directory build, and then you cd into build, and then you call your cmake, level up above that, and it fetches that cmake list.text.
Yeah. The workflow is essentially the same as it was for the previous projects. So there shouldn't be too much of a change there.
Right. So just compiling with that one change. Cool. I kind of open this up, and I see I have this executable file, which is .npc. So let's go ahead and run that. Go ahead and listen to the port. Let's see where I have the simulator at. And kind of do this MPC one right here. And this is without delay. Right. So, but let's see what it looks like. Kind of had.
Right, and so the yellow line is the polynomial fit. And the green line at the top is the fit from mod predictive control.
Right. We've kind of had these questions like, well, why does it seem like this green point is always like a forward, is ahead of the car? And I think after doing some experiments, it seems like it's just because of how the solver is returning it. It's always returning the point after the initial. If you really wanted to, if you want the point to go from the car, you could like deliberately set that point to 0, 0 if you have no delay, and it'll actually be sitting on the car and it'll come outwards. So, and then if you have the delay, you want to use the XY point that's transformed after the delay. But cool, so it's able to go at some pretty high speeds, but it's not willing to sacrifice itself to go off the track because those coefficients were so high for doing low cross-track error and error psi that it's going to slow down, even though like the reference velocity that we're giving it, it's 100. I also recently upped the speed even more to 200, and I haven't tried that yet. But I guess we could put in 200 and see what would happen. I don't know. Maybe another time. But cool. Okay. So I think we're ready to answer some questions. Yeah. So. Yes, we did cover a potential solution, sort of, without the delay. And I guess that's one of the things we could talk about right now if people are interested in.
Right, so I mean, I guess without giving out too much, you could use the equations to simulate sort of where you're going to be in the future, and then use that as your first state. Yeah. So use those same kind of transition functions that you're using in the MPC.cpp, and you'll get your next state. So
forward in time by, say, 100 milliseconds.
Yeah.
And I found that worked pretty well.
So
Let's see if we missed anything.
we'll build the project and run the code. Yeah, we just did that. So
All right.
yes, yeah.
Check that one off the list. Oh yeah, no problem, Sandro. Says thank you for the walkthrough.
So well, what else sort of should students know?
Well, I feel like we covered in detail kind of how the solver works. Also, there's that recent classroom concept that was added that covers that in even more depth.
Yeah. So maybe we could sort of show that right now.
Yeah.
We're waiting for.
This concept right here.
Right. So we recently put in a solution for the quiz. And so here we essentially just talk about how we set n and dt. And so what might happen if you changed it. So if you set n to like 100, for example, the simulation runs pretty slow. Like you wouldn't want to do this in the actual project because then your car will just crash into the lake every single time, pretty much. Although if you do have one that's sets it to a high value and it works, like I'd like to see it.
Yes.
Right. So yeah, we go over the function here. So one more thing I like to say about this is that this isn't called directly in our code. Like we never use this function directly in our code, but it is used by the solver. Right. So that's sort of where that comes in. Right. And so here's another sort of part. So right. So we have the variables here in our state. We also have the control inputs, delta and a. And the solver takes in a one-dimensional vector. So that's sort of why we have to pack like it all in one vector, even though it might be nicer to sort of use a 2D
Oh yeah.
matrix, right?
Mm-hmm.
But and anyway, so like here's sort of like how it works. So if n is 25. So like vars 0 to vars 24, that would be x1 to x25. Vars 25 to 49 would be y1 to y25, and we sort of go on like that. And then here we see we only have 24 values for delta and a. And that's because we're sort of doing...
Leaving out that boundary.
Yeah, right. So those come in sort of in between the states, that their transitions to the next state.
Right.
Right. Yeah. So the cost function, we sort of went over that, and here as well, minimize the change rate, and this minimizes the value gap between sequential actuations. Right.
There's some more equations about doing the transitions.
Change the lower bound, upper bound, over that. Yeah, so yeah, like pretty much a lot of it is what we talked about in the walkthrough here. And then for the initial quiz too, we also sort of have put more details about what the solver does, and also what CPP-AD does, and sort of why you have to sort of call it like this instead of like this. Sort of because CPP-AD builds a graph or a tape, sort of similar to how like TensorFlow does. And then it uses that to calculate the gradients, derivatives, Jacobians, Hessians.
There's a lot of those.
Yeah, yeah. And the solver itself uses Jacobians and Hessians. So yeah, so those are important, and they would be very tedious to calculate by hand, and we would probably get it wrong quite a bit of the time, or at least I would. But and yeah, so this just makes sure that it puts it on the internal tape so that it knows. So it's like, okay, let's calculate the derivatives for this guy. Right. Yeah, so then the sort of the structure of the project, so the two main sort of functions in main.cpp, or not main.cpp.
MPC.cpp?
Yeah, MPC.cpp are the solve method and the fg.eval class. And then sort of we sort of go here in detail about what they sort of do. Similar thing to the solution where we talk about how it's laid out, the constraints, gone over that. Yeah. See if there's another question.
Oh yeah. Let's go ahead and stop sharing. Looks like there's not any other questions, so.
All right, well, let's go back to screen share because there was the other concept that I wanted to sort of go over. All right, so the next concept, tuning model predictive control. And this sort of just talks about tuning the parameters for the cost function so that it sort of behaves more of how you want it to. So you're probably really used to tuning parameters from the PID project. And don't worry, there's plenty of tuning here as well. All controllers require tuning, so it's something that you kind of just have to deal with, for better or for worse. But yeah, so here, here, for example, like this looks pretty good. Like it's kind of smooth here, and it goes like that. And I mean, that looks like it's a pretty good solution to me, right? Does that like yeah. I mean, yeah, can't get much better than that, right? So, but if we look at the steering value here, we see that it starts off at -25, and then it just shoots right away to +25, and that will actually create a
huge amount of jerk.
Yeah. So if that happens in the actual simulator, the car will actually crash into a tree or go into the lake, depending on which way it turns. And then sort of we see that, and then sort of stays at that, and then kind of this is a little bit smoother, but it
still has all those sharp edges.
Yeah, and so what we can do to sort of make this smoother is to add values to different parts of the cost function. So one place that we could add this is at the part where we're concerned about sequential So like the previous delta value being similar to the next delta value. And so that's one place that we could add. So here we times that by 100. So say it's like, hey, we want to sort of pay more attention to this part. And then so even just multiplying it by 100, we see that it's smoother. Like it's still kind of, I mean, it still jumps quite a bit, but it's smoother. And then we could keep multiplying it times 500. I mean, now it's even smoother, right? So, and that's sort of the general idea. So sort of just multiplying those values, and then sort of it changes of the behavior of the car.
You could even go even further and do the rate of change of that and make sure that they're similar. So like
Yeah.
the derivatives and everything. And that would probably help that one little corner out on the bottom left right there. That seems to be pretty consistently sharp even on the very bottom. But if you start talking about
here it's right?
Yeah, but I still wouldn't want to run into that. I don't know.
Yeah, that's a fair point.
Yeah. So if you want to go the extra mile, you could do the slopes. Make sure those slopes are pretty similar too.
Yeah.
Yeah.
Right.
Cool. All right. Well, it looks like there's no further questions, so maybe we should just end early.
I think we could wait 5 minutes.
Okay.
It is to 5:30.
All right.
Give the people what they want. Let's see.
In the meantime, should we try running the simulator at 200?
Yeah, sure. Let's do it.
All right. Let's see what happens. I think this is the newest version of simulator.
Oh, there was one.
Yeah, I saw that.
Was there a question?
No.
Okay. All right. All right, guys. So we're gonna try running the solution at 200 now, and see if it crashes into the lake or not. This is the version of the simulator that can go to 200, right?
Yeah, it's version 1.4, so that's the newest one.
Maybe, right. If this doesn't work, maybe you could also show a preview of the path planning project.
Oh yeah, and how that could tie into MPC as well.
Right. So we'll try this real quick, and then we'll show the path planning project really quick as well.
Let's see what happens here.
All right.
See if we can go over 100.
Right. Yeah.
And still go around the corners.
We don't have latency, so.
Yeah, it doesn't have latency.
So maybe it'll work out better than we think.
95 already on the bridge. 99.
Ooh,
oh man, so close. All right.
All right.
You probably want to tune it somewhere. Oh, is it gonna like find its way back onto the track?
Back to tuning.
So what you'd want to do right then is go to the cost function and make those coefficients even higher is something I would do, just to make sure that it could slow down. But yeah, it's something fun to play with.
Yeah, all right. Let's show the path planning real quick. Great. So in the path planning project, we have a new track, the highway track. So fans of the lake track will be sad They'll be very disappointed that we have a new track, but the highway track's pretty nice. So
and it's going all the way up to
decent.
100 right now.
Oh. All right, so I thought it could make that turn, but all right. Right, so what's going on here?
The car is trying to pass cars at the moment,
Yeah.
but drive as smooth as it can. So it has
Right.
this acceleration T, which is a tangential acceleration. It has acceleration N, which is the normal acceleration. So it's like the centripetal force you would feel when you're going around a corner like here.
Oh.
And then there's total acceleration, which is just the magnitude of those two components. And then there's jerk. But jerk right now is being accessed every 20 milliseconds. So it's probably it's probably a little bit more jumpy and sensitive than it needs to be right now. It could probably be smooth to 1 second. But in this project, basically you're trying to write the C++ code that's going to generate this path and make sure it's smooth and able to navigate this highway with these other cars that want to go fast or slow, and all sorts of different speed variations around 50 miles per hour, which is the speed limit, but these guys, don't always obey that. And they can change lanes, and so you're just trying to make it all the way around the track, basically. And yeah, you're generating this path to follow, and you're using a perfect controller in this sense, so that's why these acceleration values are really important. But you could tie this in with MPC and give the MPC controller this path that you're generating, and pretty similar to the MPC project itself. Try to make sure that the car follows it. This path is kind of made up of individual points. The spacing is actually what makes the car go faster or slower. If these points are really spaced far apart, then the car will be going fast. If they're really close together, it'll be going slow. And so you'd have to deal with some separate things with MPC to kind of make sure that it's, instead of maybe being close to the line itself, maybe these points at certain time segments to actually generate like the cost function for how fast it should be going. But yeah, probably just stop it right there. And that's the path planning project sneak preview, and looking to beta test it right now, just getting that staged. So cool.
Let's see if there's a question or two we could answer before we go.
Yeah.
Is it okay for the car to drive on restricted area or past the lane lines for solution?
Well, what do you think, Dom? You did the rubric.
Well, I think it's okay as long as it doesn't go on the curb, right? So the strip lines, I don't believe, are part of the curve.
Right. It shouldn't go up on one of the bumpers.
Right. Yeah. So as long as it doesn't do that.
Yeah. The striped line, yeah, no problem. That's just like a painted decal.
Yeah.
Basically, just want to be smooth. If it went up on a bump, that would cause like a lot of jerks. So I think that would be an uncomfortable ride.
Right.
Yeah. Cool. All right, guys. Thanks for joining today, and we'll end it here. See you later in the classroom. All right.
See you guys.
Bye.
Thanks for joining.
Drive safe.